Well, this lesson, resolution Rayleigh criteria, is a continuation of single-slit diffraction. The key details from single-slit diffraction are what the profile looks like and the angle that occurs between the central bright spot or central maximum and the first minimum. That was really the focus of the details within single-slit diffraction. So now we're going to apply it to this concept of resolution. So let's look at that again, because we've talked about it before when we first introduced the concept of diffraction. So a resolution, one way of looking at it, is the ability for an eye or any optical instrument to produce separate images from two or more point sources, let's say, okay, that are, well, they don't have to be close together, but a classic example are headlights in a car. If a car is close enough, you can clearly see two headlights. However, if it gets a little further away, then those headlights start to merge. We can still tell there's two. And then if it's far away enough yet, then it looks like one headlight. Why? Why would two sources of light look like one? That's not obvious why they would occur. And this is not just some trivial matter involving car lights. In astronomy, this is crucial. If I'm looking at some star system through a telescope, it might look like one star system when in fact there are two of them, but we're not able to resolve them. Or something even more subtle. If you look in a nighttime sky at a star, it always looks like a point source. There's no diameter to it. Why is that if stars have a diameter to it? Or when you look at the moon, you can clearly see a left edge versus a right edge. In other words, it has diameter. So why is it we can see disks, like with planets or the moon, but with stars, they always appear as point sources? That's ultimately a resolution problem, and resolution problems are ultimately a diffraction and interference issue. And so we want to understand why that is, because that's not immediately obvious. Okay, so let's take the eye. The eye is an aperture. Well, more specifically, the pupil of the eye acts an aperture, and so when light passes through it, we have single-slit diffraction that can occur, and we can form a interference pattern on the retina. Okay. Now let's say we have two sources of light that are acting, shining in our eye. So let's go down to the diagram right here. Okay. So I have one source of light. It passes through the eye, and it will start diffracting and forming an interference pattern, single-slit diffraction, and it forms an interference pattern that looks, let's say, like that. There it is, a big central bright spot, and then the other maxima and minima, tail off, are really insignificant. And then if we have another light source that comes as separated from the first one by some distance, let's say x, it will form its own interference pattern. And in your retina, you have two interference patterns. Well, if they're widely separated within the eye, within the retinal cells, then you can tell there must be two sources of light. However, if you look at the second situation where these guys are much closer together, called x prime, now if you look at their respective interference patterns, you'll see that those interference patterns are close to being completely overlapping. And if you're close to being completely overlapping, then one retinal cell can't tell the difference from its neighbor. And so you would see it as one light source. So that's ultimately, so if there's, I'll back up to this bullet, if there's significant overlap in interference patterns from both objects, then the eye cannot resolve the two, hence only one object will be seen. So we want to understand is then what is the criteria for which we can determine if there's two or one. And that actually depends on 4 different measurements, 2 that go with the actual light sources themselves, and 2 that are based on the mechanism that's seeing the light sources. In other words, the eye or a lens, a telescope, etc. Okay, and we have to make sure we understand the role of each one and the factors that affect them. That's where things can get confusing. So, the key to understanding this is called the Rayleigh Criteria. And again, I'm going to use this diagram when I'm erasing the marks to help us understand it. All right. So it basically says Rayleigh Criteria: 2 images are just resolved when the first minimum of a diffraction pattern is located on top of the maximum of the other. So we have one and then the other. So we need two sources of light for this to be an issue. If you recall from before, the diffraction pattern for a source of light passing through a single slit looks something like this. Okay, and so here is the maximum, here is the first minimum. Now that's just for one light source. We're talking about two, so let's break this down a little bit more. Okay, so let's go up to these profiles. So here is the profile of two interference patterns that can be resolved. Let me show you how the Rayleigh criteria applies to this. If I take the leftmost peak and I draw its full interference pattern, okay, here are the dots, dashed lines go with that. The first minimum is right there. Okay, that's what the minimum we're referring to in that first blank is. Now, if we look at the other interference pattern, we want to understand where its maximum is. That's right there. And we can see that this maximum is not quite overlapped this minimum, so they're resolved. They're far enough apart that we can tell that there are two distinct sources of light. At the Rayleigh criteria itself, which is the middle diagram, again, if we look at the left peak and draw its interference pattern, here is the first minimum, here is the peak of the other one, and we see that they're exactly on top of the other. So at this point, we can just barely resolve the two objects. So this would be something that is just barely resolvable. They're starting to merge, but you can still tell there's two distinct sources of light. And then for the unresolved, the third situation, if we look at the first minimum of one of the interference patterns, again right here, and we look at the maximum of the other interference pattern, we can see that they've overshot one another. Okay, this guy is past being overlapped with this one, so they cannot tell. You cannot tell the difference between them. So note the difference between this situation here and this situation here. They have not quite yet overlapped, and the resolved part here, they're past being overlapped, if you will. And the Rayleigh criteria, they are exactly overlapped. Okay, so how do we put it all together now? This is where things can get kind of confusing. So pay close attention, come in with questions, and whatever confuses you. The basic idea is this. We have two different angles we want to compare. An angle subtended by the objects themselves, the sources of light, and then the resolution angle based on Rayleigh criteria. And if the theta object is greater than the resolution angle, then we can tell the two apart, right? Then the two objects can be resolved. So let's describe them mathematically. Let's go to the bottom here. Let's start with theta object. Okay, theta object is nothing more. So if we go up to this diagram here, we have our two sources of light, and they form an angle. Theta object is referenced by here, which is the same as that angle there. Well, how do we calculate it? Well, it's a fairly simple geometry. Let's say again they are a certain distance apart from one another, and they are a certain distance away from the eye or the camera or the lens. With basically making right triangles out of them, we've got to realize that this angle is generally going to be very, very tiny. That angle is nothing more than x over L. Okay? We've seen that before with double slit diffraction. The resolution angle, theta min, is based on, we want that to be greater than theta min, is based on the Rayleigh criteria. The Rayleigh criteria says when the minimum of one overlaps the maximum of another, then we get just barely resolved. Well, if you really stop and think about that, then here is the minimum of one. When it overlaps the maximum of the other, the angle is nothing more than the same angle as between here and here. That's theta min. And we learned that theta min is nothing more than the wavelength divided by b. That was from the previous lesson. So let me repeat that because that's easily lost in this whole discussion. The Rayleigh criteria says the peak of one just overlaps the min of the other, the red. Well, that angle of separation is nothing more than the angle between here by symmetry. And so that's where that equation comes from. So in other words, this is going to be lambda over b. Now there might be a 1.22 in there because of the geometry, but we're not worried about that. So all told, we want this. Okay? And so we can look at the second arrow here. Let's say we want to maximize our ability to be able to tell something apart. In astronomy, we can only control our telescopes. In a case of looking at distant lights, well, we can choose how far away we are from the lights, or we can choose the wavelength that we see. So there are 4 things that can be affected. 2 that increase theta object, and 2 that decrease, no, I said decrease, theta min. Okay, so if I want to do the theta min part, I want that to be really small, then I want one of 2 things. I want a large aperture. Okay, bigger b is, smaller theta is, and or I want a short wavelength. So in astronomy, if we choose to look at something in the violet part of the spectrum, we'll get much better resolution than, let's say, in the red part of the spectrum. Or more likely is if we want to look at an infrared part of the spectrum, which is long wavelengths, we're going to have a hard time resolving things than in the visible part of the spectrum. So to compensate for that, let's say we want to look at an object in infrared where this is going to be longer than normal, the wavelength, then we got to make sure we have a very, very large aperture, a large telescope, or telescopes that are 2 telescopes that are separated by a large distance. From the theta object point of view, we want this to be a maximum, so there's 2 things we can do. We can decrease, or maybe that's not the right word for this context, but small separation distance, right? If our equation is this, the smaller this is, all right, so I made a mistake on that earlier. I want a large separation distance x, and I want a short distance to the object d. I used L over here. This should be a d. Okay, so that's theta object. Okay, so to sum up, and we'll do in the next video, we'll do some practice with this. If you want to resolve 2 objects, it would be nice if the things you're looking at are close and widely apart, but very often you don't have control over that. So what you can perhaps control is the resolution angle, which is based on what you choose to look at it with, pupil, lens, etc., and the wavelength of light, which you might not have control over. So ultimately what you do have is B, so the bigger your diameter is, the more likely you will be able to resolve 2 objects. Okay, so the next lesson, again, we will look at some specific problems.